All right. Good afternoon, everybody. So, yeah, today we're doing intro to homology, which is a very fun topic. My exposure to homology so far has been through algebraic geometry, and the homology and cohomology of sheaves. So this is hopefully going to be kind of a new spin on something that I've seen before and maybe you've seen before, but maybe not. And so, yeah, we have, there's this incredibly long introduction section, and simply because this is my first time reading Hatcher, I think it's a good idea to read the whole thing, but then we'll dive further into 2.1 immediately following reading everything. There's some proofs in here and some theorems that we're going to omit, for example, the five lemma and the snake lemma, because I've proved both of those somewhere else. Uh, I think there's a link that I can maybe put in the description of this video to where I proved the snake lemma and the five lemma in VQ. I think they're appropriately labeled, but yeah, if you've never worked through it before, it's important, but otherwise, it's okay. Okay. Um, so the fundamental group pi 1 is especially useful when studying spaces of low dimension, as one would expect from its definition, which involves only maps from low dimensional spaces into X, namely loops and homotopies of loops, and maps from the unit interval across the unit interval to X. The definition in terms of objects that are at most two-dimensional manifests itself, for example, in the fact that when X is a CW complex, pi 1 only depends on the 2 skeleton of X. In view of the low-dimensional nature of the fundamental group, we should not expect it to be a very refined tool for dealing with high-dimensional spaces. Thus, it cannot distinguish between spheres S to the n with n greater than or equal to 2. This limitation to low-dimensional topology can be removed by considering the natural higher-dimensional analogs of pi 1 of x, the homotopy groups pi n of x, which are defined in terms of maps of the n-dimensional cube I to the n into x, and homotopies I to the n cross I of such maps. Not surprisingly, when x is a CW complex, pi n depends only on the n plus 1 skeleton of x, and as one might hope, homotopy groups do indeed distinguish spheres of all dimensions, since pi I of s to the n is 0 for I less than n, and z for I equal to n. However, the higher dimensional homotopy groups have the serious drawback they are extremely difficult to compute in general. Even for simple spaces like spheres, the calculation of pi I of Sn for I greater than n turns out to be a huge problem. Fortunately, there is a more computable computable alternative to homotopy groups, the homology groups, Hn of x. So like pi n of x, the homology group for a CW complex, it depends only on the n plus 1 skeleton. For spheres, the homology groups Hi of Sn are isomorphic to the homotopy groups pi I of Sn in the range I less than, or I in 1 to n, but homology groups have the advantage that they are 0 for I greater than n. So the computability of homology groups does not come for free, unfortunately. The definition of homology groups is decidedly less transparent than the definition of homotopy groups. And once one gets beyond the definition, there's a certain amount of technical machinery to set up before any real calculations and applications can be given. In the exposition below, we approach the definition of the homology group by two preliminary stages, first giving a few motivating examples non-rigorously, then constructing a restricted model of homology theory known as simplicial homology, before plunging into the general theory, singular homology. After the definition of singular homology has been assimilated, the real work of establishing its basic properties begins. This takes close to 20 pages, and there is no getting around the fact that it is a substantial effort. This takes up most of the first section of the chapter, with small digressions only for two applications to classical theorems of Brouwer, the fixed point theorem and invariance of dimension. The second section of the chapter gives more applications, including the homology definition of Euler characteristic and Brouwer's notion of degree for maps from Sn to Sn. However, the main thrust of this section is towards developing techniques for calculating homology groups efficiently. The maximally efficient method is known as cellular homology, whose power comes from the fact that it is homology squared, homology defined in terms of homology. Another quite useful tool is the Meyer-Vittoris sequence, or sequences, the analog for homology of Van Kampen's theorem for the fundamental group. Another interesting feature of homology that begins to emerge after one has worked with it for a while is that it is the basic properties of homology that are used most often, and not the actual definition itself. This suggests that an axiomatic approach to homology might be possible, and is indeed the case, and in the third section of the chapter, we list the axioms which completely characterize homology groups for CW complexes. One could take the viewpoint that these rather algebraic axioms are all that really matters about homology groups, that the geometry involved in the definition of homology is secondary, needed only to show that the axiomatic theory is not vacuous. The extent to which one adopts this viewpoint is a matter of taste, and the route taken here of postponing the axioms until the theory is well established is just one of several possible approaches. The chapter then concludes with three additional options of additional topics. The first is rather brief, relating the first homology group to pi 1, while the other two contain a selection of classical applications of homology. These include the n-dimensional version of the Jordan curve theorem and the invariance of domain theorem, both due to Brouwer, along with the Lefschetz fixed point theorem. Okay, any questions on all of that? Okay. So the idea of homology. The difficulty with the higher homotopy groups, pi n, is that they are not directly computable from a cell structure as pi 1 is. For example, the 2 sphere has no cells in dimensions greater than 2, yet its n-dimensional homotopy group is non-zero for infinitely many values of n. Homology groups, by contrast, are quite directly related to cell structures and may indeed be regarded as simply an algebraization of the first layer of geometry in cell structures. How cells of dimension n attach to cells of dimension n minus 1. Let us look at some examples to see what the idea is. So consider, and now this is, I suppose, where I should draw a graph. So consider the graph that is being drawn where this is curve B, curve C, curve D, curve A, point X, point Y. So consider the graph, and we're going to call this X1. So when studying the fundamental group of X1, we consider loops formed by sequences of edges, starting and ending at a fixed base point. For example, at the base point X, the loop A, B inverse travels forward along the edge A, then backwards along B, as indicated by the exponent minus 1. A more complicated loop could be, and I'll draw this, so A, C inverse, B, D inverse, C, A inverse. A salient feature of the fundamental group is that it is generally non-abelian, which both enriches and complicates the theory. Suppose we simplify matters by abelianizing. Thus, for example, the two loops A, B inverse and B inverse A are to be regarded as equal if we make A commute with B inverse. So these two loops, A, B inverse and B inverse A, are really the same circle, just with a different choice of starting and ending loop, or starting and ending point. X for A, B inverse and Y for B inverse A. The same thing happens for all loops. Re-choosing the base point in a loop just permutes its letters cyclically, so a byproduct of abelianizing is that we no longer have to pin all of our loops down to a fixed base point. Thus, the loops become cycles with a chosen base point. Having abelianized, let us switch to additive notation, so cycles become linear combinations of edges with integer coefficients, such as a minus b plus c minus d. Let us call these linear combinations chains of edges. Some chains can be decomposed into cycles in several different ways. For example, a minus c plus b minus d is equal to a minus d plus b minus c. And if we adopt an algebraic viewpoint, then we do not want to distinguish between these different decompositions. Thus, we broaden the meaning of the term cycle to be simply any linear combination of edges for which at least one decomposition into cycles in the previous more geometric sense exists. So what is the condition for a chain to be a cycle in this more algebraic sense? A geometric cycle, thought of as a path traversed in time, is distinguished by the property that it enters each vertex the same number of times that it leaves the vertex. For an arbitrary chain, the net number of times this chain enters, a point is the sum of its integer coefficients, since each edge enters the point once. Similarly, each of the four edges leaves x once, and so the net number of times the chain enters x is minus one times the number of times it leaves the other point. Thus, the condition for a loop to be a cycle is simply that the coefficients should sum to 0. So describe this result in a way that would generalize to all graphs. Let C1 be a free abelian group with basis edges A, B, C, D, and let C0 be the free abelian group with vertices X and Y. Elements of C1, so elements of C1 are chains of edges or one-dimensional chains, and of C0 are chains of vertices. Or zero-dimensional chains. Define a homomorphism from one to the other, sending C1 to C0 by sending each basis element A, B, C, or D to y minus x, which is the vertex at the head of the edge minus the vertex at the tail. Thus, we have that partial of Ka plus Lb plus Mc plus Nd could be equal to K plus L plus M plus N y minus K plus L plus M plus N x. And the cycles are the kernel of this map. So anything where x and y zero out here land in the kernel, and so they are the cycles. It is a simple calculation to verify that a minus b, b minus c, c minus d form a basis for this kernel. So in this specific case, a minus b, b minus c, c minus d work. Okay, thus every cycle in X1 is a unique linear combination of the three most obvious cycles. By means of these three basic cycles, we convey the geometric information that the graph X1 has three visible holes, the empty spaces between four edges. So hole 1, hold 2, hold 3. Is this all making sense so far?
Yeah, we're good.
Okay. Let us now enlarge the preceding graph by attaching a 2-cell along the cycle A minus B. So what that looks like is now we are adding a surface here. And we're going to call the surface capital A. So producing a two-dimensional cell complex X2. So if we think of the 2-cell A as being oriented clockwise, then we can regard its boundary as the cycle A minus B. So this cycle is now homotopically trivial since we can contract it to a point by sliding over A. In other words, it no longer encloses a hole in X2. This suggests that we form a quotient of the group of cycles in the preceding example by factoring out the subgroup generated by the boundary A minus B. In this quotient, the cycles A minus C and B minus C, for example, become equivalent, consistent for the fact that they are homotopic in X2. Algebraically, we can now define a pair of homomorphisms, C2 by partial 2 to C1 by partial 1 to C naught, where C2 is the infinite cyclic group generated by capital A, with partial 2 of A is equal to A minus B. The map where C2, the map partial 1 is the boundary homomorphism in the previous example, and the quotient group we are interested in is the kernel of partial 1 mod the image of partial 2. So the one-dimensional cycles modulo those that are boundaries, this is the one-dimensional cycles modulo those that are boundaries. So one cycles mod A minus B. The quotient group is the homology group H1 of X2. So this is our first look at homology. The previous example can be fit into this scheme too by taking C2 to be 0 since there are no 2 cells in X1. So in this case, the first homology group of X1 is just the kernel of partial 1, which we saw was free abelian on 3 generators. In the present example, H1 of X2 is a free abelian group on 2 generators, B minus C and C minus D, expressing the geometric fact that by filling in the 2-cell A, we have reduced the number of holes in our space from 3 to 2. Right, so this is generated by B minus C, C minus D, and rather the dimension of X2 is equal to 2, meaning that we started with 3 holes, now we have 2 holes. Suppose we enlarge X2 to a space X3 by attaching a second C cell B. So now this is where it gets really complicated. So if we have our initial 1 cell here, and then we attach something that makes this a tube that is tied at both ends. This gives us a two-dimensional chain group C2 consisting of linear combinations of A and B, and the boundary homomorphism, partial 2, from C2 to C1 sends both A and B, the second thing we've added, to A minus B. So the homology group of this x3 is the same as for x2, but now partial 2 has a non-trivial kernel, the infinite cyclic group generated by A minus B. So we may view A minus B as a two-dimensional cycle generating the homology group H2 of x3. And so that's the kernel of partial 2, and that's isomorphic to C. Topologically, the cycle A minus B, capital A minus B, is the sphere formed by the cells A and B together with their common boundary circle. This spherical cycle detects the presence of a hole in X3, the missing interior of the sphere. However, since this hole is enclosed by a sphere rather than a circle, it is of a different sort from the holes detected by the first homology group of X3, which is Z cross Z, that are detected by the cycles B minus C and C minus D. So let us continue one more step and construct a complex X4 from X3 by attaching a 3-cell along the 2-sphere formed by A and B. This creates a chain group C3 generated by this 3-cell C. And we define a boundary homomorphism in the same way, sending this higher dimensional object C to A minus B, since the cycle A minus B should be viewed as the boundary of C in the same way that the one-dimensional cycle little a minus B is the boundary of capital A. Now we have a sequence of 3 boundary homomorphisms, C3 going to C2, going to C1, going to C0, and the quotient of the second homology group at X4 is the kernel of partial 2 mod the image of partial 3 is trivial. Also, the third homology group is just the kernel of the third partial, and so that's 0. The group H1 of X4 is the same as H1 of X3, namely Z cross Z, so this is the only trivial homology group, non-trivial homology group of X4. Okay, so it is clear what the general pattern of examples is. For a cell complex X, one has chain groups, which are the free abelian groups with the basis the n cells of X. There are boundary homomorphisms in terms of which one defines the homology group. And the major difficulty is how to define the boundary map in general. For n-1, this is easy. The boundary of an oriented edge is the vertex at its head minus the vertex at its tail. The next case, n-2, is also not hard, at least for cells attached along cycles that are simply loops of edges. For then, the boundary of the cell is this cycle of edges with the appropriate signs taking orientations into account. But for larger n, matters become more complicated. Even if one restricts attention to cell complexes formed from polyhedral cells with nice attaching maps, there is still the matter of orientations to sort out. The best solution to this problem seems to be to adopt an indirect approach. Arbitrary polyhedra can always be subdivided into special polyhedra called simplices. The triangle and the tetrahedron are the two-dimensional, three-dimensional instances, so there is no loss of generality. Though initially there is some loss in efficiency in restricting attention entirely to simplices. For simplices, there is no difficulty in defining boundary maps or in handling orientations, so one obtains a homology theory called simplicial homology for cell complexes built from simplexes. Still, this is a rather restricted class of spaces, and the theory itself has a certain rigidity that makes it awkward to work with. The way around these obstacles is to step back from the geometry of spaces decomposed into simplexes and to consider instead something which at first glance seems wildly more complicated, the collection of all possible continuous maps of simplexes into a given space X. These maps generate tremendously large chain groups, but the quotients called singular homology groups turn out to be much, much smaller, at least for reasonably nice spaces X. In particular, for spaces like those in the 4 examples above, the singular homology groups coincide with the homology groups we computed from the cellular chains. And, as we shall see later in this chapter, singular homology allows one to define these nice cellular homology groups for all cell complexes, and in particular to solve the problem of defining the boundary maps for cellular chains. Okay, so does this all make sense so far?
Yeah, I think the walking through that kind of one example helped a lot.
Yeah, I know I wasn't writing a ton, but hopefully it still made sense. Um, um, okay, so yeah, 2.1 simplicial homology and then singular homology. Okay, the most important homology theory in algebraic topology, and the one we shall be studying almost exclusively, is called singular homology. But before beginning the development of singular homology, we will first introduce a more primitive version called simplicial homology to give some idea of how the technical apparatus works in a smaller scale setting. The natural domain of definition for simplicial homology is a class of spaces we call delta complexes, which are a modest generalization of the more classical notion of a simplicial complex. Okay, so delta complexes. We begin with three examples: the torus, the projective plane, and the Klein bottle. Each of these surfaces can be obtained in the following way that is very weird. Okay, so we're taking a square that has a diagonal line and presumably five vertices that I'm going to go ahead and label like so. Um, and it seems that the names of, okay, so we have A, B, B, and C, and the orientation potentially changes. Then this is a second cell U. This is a second cell L. And then our vertices kind of get flipped around based off of the orientation. Okay, so starting, we have torus, we have the real projective plane, and then we have the Klein bottle. Wow, that was a terrible K. Okay, and so now what we're going to do is we're going to set the orientation. So this orientation is the easy one. This is something that we've seen in general topology, where we have V, 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 V. Then here we need to spice it up a little bit. So both of the A's stay the same, but then we switch the orientation here and get V, W, W, V. And then here in the Klein bottle, we have V, V, oh, and the diagonal is straightforward. V, 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 and then just a slight change going on. So this is nice, this is nice, this is nice, this is nice, this is not nice. Okay. So each of these surfaces can be constructed from two triangles by identifying certain pairs of edges. In a similar fashion, a polygon with any number of sides can be cut along the diagonals into triangles, and so, in fact, all of the closed surfaces can be considered to be constructed from triangles by identifying edges. Then we have a single building block, the triangle, from which all surfaces can be constructed. Using only triangles, we could also construct a large class of two-dimensional spaces that are not surfaces in the strict sense by allowing um, by allowing more than two edges to be identified together at the same time. Okay, delta complexes are a generalization of this idea using the n-dimensional analog of the triangle, the n-simplex. This is the smallest convex set in R to the m, containing n plus 1 points. So definition, n simplex is the smallest convex set in Rm containing m plus 1 points v naught through vn that do not lie in a hyperplane of dimension less than n. Or by a hyperplane, we mean the set of solutions of a system of linear equations. An equivalent condition would be that the vectors v1 minus v naught, etc., vn minus v naught are linearly independent. What is going on? V2 minus v naught, vn minus v naught are linearly independent. Where the points vi are vertices of the simplex, and the simplex itself is a set of coordinates. So, for example, there is the standard unit simplex is the pair of coordinates ti squared equals 0 for all I. Okay, whose vertices are the unit vectors along the coordinate axes. For the purpose of homology, it will be really important to keep track of the order of the vertices of the simplex, so n simplex will really mean n simplex with an ordering of its vertices. A byproduct of ordering the vertices of a simplex is that this determines orientations of edges vi, vj according to the increasing subscripts as shown in the preceding figures. I didn't draw those out. It's not that crazy, honestly. Specifying the ordering of the vertices also determines a canonical linear homeomorphism from the standard n simplex onto any other n simplex, preserving the order of vertices, namely by sending the t naught to tn down to the sum ti vi. So basically, we can scale things by coordinates. So this is a homeo. The coefficients ti are the barycentric coordinates of the point sum ti vi in n. So really, it's this scaling factor that we're looking at. Okay. So a face of a simplex is the subsimplex with vertices any non-empty subset of the VIs. We adopt the convention that the vertices of a face will always be ordered according to their order in the larger simplex. The fast definition of a delta complex is that it is a quotient space of a collection of disjoint simplexes obtained by identifying certain faces via the canonical linear homeomorphisms that preserve the ordering of vertices. Somewhat more formally, the data one starts with is a collection of disjoint simplexes. So delta complex starts with a alpha n of various dimensions with certain sets fi faces of the delta alpha n's which have the same dimension. Then one forms a quotient space of the disjoint union of delta alpha n mod I in I. the faces. And this is the delta complex. And that is accomplished by the canonical linear homeomorphisms between each of the faces. Notice that the data determining a delta complex is purely combinatorial with no topology involved. Constructing a delta complex is like building something from a kit of pre-cut parts that only needs to be snapped together to follow the instructions. The representations of the torus, projective plane, and Klein bottle as shown are in fact delta complex structures because the indicated orientations of the three edges of each triangle are compatible with a unique ordering of the vertices of the triangle. And so really that's what we mean when we like put an arrow there. In general, the edges in any delta complex inherit well-defined orientations from the ordering of the vertices of the simplices from which X is built. These orientations are not completely arbitrary, since the orientations of the various edges in the boundary of each n-simplex of X must be related just as they are in a simplex, consistent with the ordering of vertices. It's not hard to check that this compatibility condition on orientations amounts to requiring that no two simplex has its edges oriented cyclically, consistent with a clockwise or counterclockwise traversal of the three edges. Notice that when the edges of a simplex are compatibly oriented, these orientations uniquely determine the ordering of the vertices. In the case of one-dimensional delta complexes, let's see, condition on orientations of edges is vacuous. In the torus and Klein bottle examples, everything is identified, so certain identifications of points in the boundary of a single simplex are allowed. As a more extreme example, we could construct a delta complex from a two-simplex by identifying all three of its edges together, preserving the orientations of these edges. It is an interesting exercise to see that these identifications can actually be performed in R3 with quite a bit of stretching and bending of the two-simplex. The resulting space is sometimes called the dunce cap. It's kind of like the house with two rooms from chapter 0. It's contractible, but not in any obvious way. Since the face identifications that produce a delta complex always preserve the ordering of the vertices, these identifications never result in two distinct points in the interior of a face being identified in X. That means that the delta complex X as a set is the disjoint union of a collection of open simplices, simplexes with all their proper faces deleted. Each such open simplex of dimension n, so okay, definition for the first time and forever, open simplex E alpha n is delta alpha n with proper faces deleted. Okay, comes equipped with a canonical map, sigma alpha from delta n to X, restricting to a homeomorphism from the interior of delta n onto E alpha n. Namely, the closure of E alpha n is the quotient of one of the simplices from which X was constructed, or of a face of one of the simplices, and sigma alpha is the quotient map from this simplex or face to X. In the appendix, we show that the open simplices are the cells of a CW structure with characteristic maps, sigma alpha, but we call this the characteristic map for E alpha n. Okay. All right. So, any questions so far? Okay. So our goal now is to define these simplicial homology groups of a delta complex X. So let delta n of X be the free abelian group with basis E alpha n of X. Elements of delta n are n chains. Can be written as sums or formal sums over alpha, n alpha, e to the n alpha, with coefficients n alpha in z. Equivalently, we could write that this is still summing over alpha, n alpha, sigma alpha, um, with image of sigma alpha equal the closure of E alpha n. Okay, this is doing the same thing that we were doing up here. This is just a really weird way to say it. I like the algebraic geometry way of this better. As one can see in the next figure, which I'll draw out, the boundary of the n simplex, v0 through vn, consists of the various n minus 1 dimensional simplexes where we delete vertices from the sequence. In terms of chains, we might then wish to say that the boundary of v0 through vn is the n minus 1 chain formed by the sum of faces v0 to vn, where vi hat denotes delta alpha n set minus vi. However, it turns out to be better to insert certain signs and instead let the boundary of the simplex, better boundary, is the sum over I minus 1 to the I of V0 through Vn. Heuristically, the signs are inserted to take orientations into account so that the faces of a simplex are coherently oriented. So the idea is just that, going back to our first example, if this is x, this is y, this is plus 1, this is minus 1. So as an example, that's in the figure, if we have v0 to v1, and we have something that goes over like so, then we'll subtract at v0 and add at v1 so that the boundary is the class v1 minus v0. Similarly, if we have a triangle where we have v0, v1, v2, we go like this, and it looks kind of like this. Then the boundary of v0, v1, v2 ends up being v1, v2 minus v0, v2 plus v0, v1. And this generalizes on out, where if we have some kind of quadrature going on here, and presumably goes like that, and we go around this way, and it's kind of hard to show this. I don't know. But this is V naught, V1, V2, V3, and the boundary of this simplex is V1, V2, V3 minus V naught, V2, V3 plus V naught, V1, V2, no, V3 minus V naught, V1, V2. In the last case, the orientations of the two hidden faces are counterclockwise when viewed from outside the 3 simplex. So with this geometry in mind, we define for a general complex, or general delta complex X, a boundary homomorphism delta n from, there's not delta n, partial n, from the n, n complex to the n minus 1 complex by specifying its values on basis elements, namely that this looks like minus 1 to the I of sigma alpha restricted to notice that the right-hand side of this equation does indeed lie in delta n minus 1 x, since each restriction is the characteristic map of an n minus 1 simplex of x. Okay, so is this like something that is well defined? Like what we're doing is we are going over to the closure of the n minus 1 e n alpha structure. So we're looking kind of at like the embedding of en alpha in the n minus 1 complex. Okay, I'm taking silence to be a good thing here. Um, so lemma 2.1, we have that the composition, rather the chain here, n minus 2 is exact. Really the way this is phrased is that it's 0, right? So what we want to say is that no, it's not exact. It's a complex. That's weird. Is a chain complex. I'll add, generally when we say chain complex, we define it by saying that partial n minus 1 partial n equals 0. But geometrically what we're saying is we're taking our faces here, taking faces to their boundaries, and these boundaries get set to points. and those points are 0. So it's like deconstructing, kind of. So like geometrically, hopefully that makes sense. I will say that this proof is just kind of messy and not very well done, and he doesn't finish it. Um, I don't know. This is how we define a chain complex. I don't think that's worth like continuing. But the algebraic situation is that we now have a sequence of homomorphisms. So much broader definition that we will use for the rest of our lives is that Cn plus 1 gets mapped by boundary n plus 1 to Cn by boundary n to Cn minus 1 to C1, which goes by partial 1 to C0, which goes to 0. And we'll call this partial 0, but really we mean it's the 0 map. And then with boundary n plus 1, I think he has that in the wrong order. That's the order for cohomology. It's boundary n plus 1. No, I read it wrong. Yeah, boundary n plus 1, boundary n equals 0. Yeah. Okay. Is a chain complex. I'm going to pretty much always call this C bullet. So if you ever see me say like something like HI C bullet, that means it's the ith cohomology group at the ith entry of this thing, because we're looking at the dimensional data at I. It's worth noting for people who have experience with this stuff that are watching this, that this of course induces a long exact, like short exact sequences induce long exact sequences in homology and cohomology. But the long sequence induced at each Cn is not something that we typically care about as much, at least where I come from. So such a sequence is called a chain complex. Note that we have extended the sequence by a 0 at the right end. And so, yeah. Then we can define the nth homology group is the kernel of partial n. That looks like a scheme. No, not a scheme. Mod partial n plus 1. So elements of the kernel are called cycles. And then of the image are boundaries. And elements of each homology group are cosets of the image called homology classes. Two cycles representing the same homology class are said to be homologous. So def. So two classes are homologous if same in HN. This means their difference is by a boundary. Okay, so returning to the case that each of the CNs is delta n of x, the homology group will be denoted, and maybe this isn't a definition, but rather notation, but HN delta of x is the nth simplicial homology group of x. Okay, so we will finish this off with, I think, 3 examples that we'll do. And then we will move on next time to singular homology, which is the much more interesting example, and get gets us into kind of the weeds of things with homological algebra. Okay, so if X is the circle with vertex 0 cell V and edge E, then delta naught of S1 and delta 1 of S1 are both identified with Z, and the boundary map is 0. Since partial E is equal to V minus V. Then the groups delta N S1 are just 0. And we can picture, I know we're really picturing this as just the end of a right exact sequence, long exact sequence. But yeah, so basically there's no simplexes in these dimensions. And so the nth simplicial homology group of the circle is Z for n equals 0 or 1, and 0 for n greater than or equal to 2. Okay. Yeah, this is an illustration of the general fact that if boundary maps in a chain complex are all 0, then the homology groups of the complex are isomorphic to the chain groups themselves. Yeah, makes sense, because then it's kernel mod image. So, okay, in a more interesting example, consider X is the torus with the delta complex structure pictured earlier, having 1 vertex, 3 edges A, B, C, and 2 simplexes U and L. So just a reminder, it looks like V, V, W, W. Nope. That was wrong. I was thinking projective space. Okay. So as pictured in the previous example, so partial 1 is 0. So the 0th homology, simplicial homology group of the torus is just Z. Then partial 2 of U, we had said was going to be something like A plus B minus C. So A plus B minus C. Or A, oops, or A, B plus A minus C would work. And so this is, like I just showed, the same map for both U and L. And since we have a basis for this, A, B, A plus B minus C, delta 1 of T, then H1 of T is isomorphic to Z direct sum Z with basis the homology classes A, B, because we're just forgetting C. and embedding down. Since there are no three simplices, um, H2 of the torus is the kernel of partial 2. Um, and this is going to be the loops on the surface, and so we should just get infinite cyclic generated by U minus L. Yeah, so U minus L. And so we get the classification that the nth homology groups are isomorphic to Z, sum Z, Z or 0, n equals 1, n equals 0 or 2, or n is greater than or equal to 3. Okay, our final example is X is real projective space, which I also have here. And the main difference in identification is that we fold over B and B when attaching it to itself. So we get like this twist going on. Okay, then the image of partial 1 attaching attaching the 1 simplex to the 0 skeleton is generated by W minus V. Yeah, it is W minus V. And so the image, kernel mod the image of um, okay. Oh, the kernel is gonna be the 0 map, right? Oh, okay, yeah. So then it's just the whole thing mod the image, which is isomorphic to Z with either vertex as generator. Um, since partial 2 of U is minus A plus B plus C minus A plus B. I think I wrote that wrong. Because this would work. Minus A. No, that wouldn't work. Minus A plus C plus B. Okay, no, that does work. You just have to take it as a Abelian. And partial 2 of L is A minus B plus C. So A minus C. Hold on. A.
You have the projective space diagram written incorrectly, I think. I think
No,
A,
it's
right? Because it should be.
this is minus B plus C plus
Oh wait, nope.
O
Never mind, never mind. You're right. You're right. You're right. You f. Uh. Wait. Hold on.
minus
Sorry.
B minus B plus C plus A.
Minus B plus C minus A. What? Wait. A. But it's A minus B. A minus. That doesn't make sense.
That doesn't make sense.
Yeah, oh, I see.
Um,
I see. You in the book you flipped B, but you're actually supposed to flip the A's, I think. Wait, no, A B's are flipped too.
yeah.
Oh, I wrote it wrong. That's why. Hold on, I flipped it. Uh, uh,
At any rate, the point of this
yeah,
is
yeah,
that it
yeah,
has
yeah,
something to do with like using all three basis elements.
yeah.
So since all three are necessary, partial two is injective um, to delta three. Um, and so since it's injective, then kernel of partial two is zero, and the homology group. No, sorry, this is to delta one. I'm thinking cohomology. Um, RP2 is zero. Further, the kernel of partial one. Yeah, way to switch that. Is isomorphic to z direct some z because it's generated by two things, I guess. With basis a minus b. Oh, and c. Um, yeah, that makes sense. And so then H1, wait, didn't we already define? No, H1 is isomorphic to Z mod 2. Yeah. Okay. Simplicial homology is a lot more complicated than actual homology, in my opinion. Um, Having worked with this in it, like, okay, the introduction I had to this was through algebraic geometry. Algebraic geometry says basically throw away the geometry, look purely at the algebra. The algebra works out nicely. This is something that you can identify typically with linear transformations. This is not that. This is really messy and kind of rigid, like it said it would be in the introduction. So I guess it delivered. Um, yeah. Either way, we're done with it. We don't ever necessarily have to use it again. Next time we will look at singular homology, and that will be a much nicer property. There's also, like I said, going to be a lot of things that we can just kind of breeze through because I think you know it, and I know that I know it. Um, so once we get up to exact sequences and like the Hom functor, although that should come at the start of a later thing. Um, to be very clear, homology is still messy no matter what. It's just this is a particularly messy formulation, I think, in my opinion. Okay, cool. I'm gonna go ahead and stop the recording.